All right, good evening. My name is Mike Joslin. I did my project on the application of the revised universal soil loss equation to study the effects of the 2011 Wallow Fire on soil loss. So the Wallow Fire began on the 29th of May, 2011 from an unattended campfire. It was fully contained by the 8th of July, 2011, and it burned approximately 535,000 acres, making it the largest wildfire in Arizona history. Immediately after a wildfire takes place, one of the immediate concerns is the increased risk of soil erosion because of vegetation loss. Here's a brief outline of my presentation. I'll go over the study area. I'll introduce the revised universal soil loss equation. I'll describe the objectives of my study. I'll go over the 5 soil loss factors that the equation uses, and I'll go over how I evaluated each of them. Then I'll end with results and my conclusions. But the study area that we used was defined by the Monitoring Trends and Burn Severity data set. Monitoring Trends and Burn Severity is a project which began in 2004 to map all wildfires in the United States. Part of the data set contained a wildfire boundary, and that will serve as our study area. It's located in east central Arizona with a small portion extending into New Mexico. The data set also provided a burn severity map, which broke up the study area into 5 different burn severity classes. And the classes were developed based on the change in the normalized burn ratio from 2 Landsat images taken at 1 year apart before and after the fire. We will use these burn severity classes in analyzing our results later on. Right, the revised universal soil loss equation is an updated version of the universal soil loss equation, which was originally developed to estimate erosion on small agricultural plots. It is defined by the equation on the right, which takes into account 5 soil loss factors, which include rainfall, slope length and slope angle, soil erodibility, vegetation cover, and support practices. These 5 factors are multiplied together to get A, which is the total amount of soil erosion measured in tons per acre per year. This equation can be applied with GIS by creating rasters which represent each factor and then multiplying them together to assess total soil loss. So the objectives of the study were to see how the Wallow Fire affected soil loss. And to do this, I applied the revised universal soil loss equation both before and after the fire took place. The vegetation cover factor, represented by C, was estimated using the Normalized Difference Vegetation Index from Landsat images before and after the fire took place. I now go over how I assess each of the soil erosion factors. The R factor, rainfall erosivity, was derived from a rainfall erosivity map published in the Revised Universal Soil Loss Equation Handbook. The map was scanned and digitized, and a raster shown here was created using Topo to Raster tool. The LS factor, the slope length and slope angle factor, was calculated using a 10-meter DM of the study area. This DM was used to create a slope angle and flow accumulation raster. As advised in previous literature, flow accumulation values over 120 and slope angle values over 12 degrees were excluded from analysis. Slope angle and flow accumulation, as well as the following 2 equations, were used to estimate L and S, where L is the slope length factor, which is calculated using A_S, which is the size of the upland catchment area, which is calculated by multiplying the DEM cell size by the flow accumulation value. And then S is the slope angle factor, where beta is the slope angle in degrees. And for both of these equations, a high slope angle value or a high flow accumulation value corresponds to a higher L or S value, and in turn, a higher potential for erosion. Both of the, after L and S are calculated, they're multiplied together to create one LS factor raster that's shown here. Areas in green were the areas that were excluded from analysis because they had slope angle values over 12 degrees or flow accumulation values over 120. The K factor, representing soil erodibility, is determined by the texture and organic content of the soil. The values for the K factor are derived from the Digital General Soil Map of the United States, published by the Natural Resource Conservation Service. The K factor values were extracted from the data set and converted to the RUSLE format shown here. The C factor represents vegetation cover, and it was estimated using 2 Landsat 5 images from the 14th of May and the 2nd of August 2011. The first step in determining the C factor was to calculate the Normalized Difference Vegetation Index, or NDVI. NDVI is a measure of vegetation health and is calculated using near-infrared and red radiation and the following equation. This gave us the following 2 NDVI images. After NDVI is calculated, the values need to be converted to C factor values. This was done with the following equation, which was first developed for a soil erosion study in Taiwan in 2002 and later used by many others. This gave us the following 2 C factor rasters. The one on the left will be used for our soil erosion calculation before the fire occurred, and the one on the right afterwards. Soil erosion values, C factor values range from 0, representing high vegetation and a low potential for erosion, to 1, representing low vegetation and a high potential for erosion. The P factor is a support practice factor, and is used to represent practices that are put in place to minimize erosion. Usually these would be in an agricultural setting. And the P factor was not used in the study because none of these practices were in place before the fire occurred. So to assess total soil loss before and after the fire, all the soil erosion factors were multiplied together. This gave us the following 2 results. Results are measured in tons per acre per year. The next 2 images show the amount of change and the percent change between the 2 dates. Areas in red showing areas where the amount of evaluated soil erosion increased, and areas in green where soil erosion decreased after the fire occurred. Results are also shown in the table on the right. The top of the table shows results for the entire study area, while the rest of the table breaks down the results based on the 5 burn severity classes described earlier. And the results show that soil erosion actually decreased approximately 20% after the fire occurred for the entire study area. However, the results were not universal. In the highest burn severity areas, soil erosion actually increased. In the moderate burn severity class, approximately 82%, and the highest burn severity class, approximately 189%. Vegetation loss showed similar results when looking at the change in NDVI. For the entire study area, NDVI changed very little, but as would be expected, areas of the highest burn severity showed decreases in NDVI, while areas of lower burn severity showed a slight increase. So now that I've assessed soil erosion for the area of the Wallow Fire, the next question to ask is how to interpret the results. In many of the previous studies that have used the revised universal soil loss equation with GIS, many have noted that the equation has a tendency to overestimate values. The equation was originally developed for assessing erosion on small agricultural plots, but when it's applied to larger areas, it has a tendency to exaggerate values. Also, the equation only accounts for soil loss, but does not account for the deposition of that soil further down slope. And for all these reasons, many have suggested that the equation only be used to estimate the spatial distribution of erosion, and high soil loss values should only be used to identify the areas with the highest potential for erosion. So in conclusion, the study set out to determine the change in soil loss caused by the Wallow Fire. And to do this, the revised universal soil loss equation was applied both before and after the fire took place. Vegetation cover was assessed using NDVI from Landsat images on the 14th of May and the 2nd of August, 2011. The results show that there was an overall decrease in soil loss after the fire occurred. However, areas of high burn severity of the fire showed dramatic increases. Here's a list of my data sources. Any questions?